Look up at the night sky, and you're seeing only a tiny fraction of what's truly out there, a glittering curtain that hides the universe's deepest secret. For decades, astronomers have noticed something strange. Galaxies spin far too fast for the amount of visible matter inside them. They should fly apart, yet they don't. They hold together as if gripped by an invisible hand. That hand is dark matter, one of the most profound and elusive mysteries in all of science. It's the universe's greatest detective story, and we're about to dive deep into the evidence, the questions, and the astonishing implications of this hidden cosmic architecture. Imagine a universe where everything we see, the stars, the planets, the glowing clouds of interstellar gas, is just the shimmering surface of something far stranger, far richer, and almost entirely invisible. That's the world dark matter invites us into. It doesn't emit light, it doesn't reflect it, and it doesn't absorb it. Yet it shapes the fate of galaxies, guides the growth of cosmic structures, and may even hold the key to understanding the ultimate destiny of our universe. This isn't just an abstract puzzle for scientists in labs. It's a story about the hidden scaffolding of reality itself, a narrative written in gravity and shadow, waiting for us to learn how to read it. In this video, we're embarking on a journey to explore 25 mind-bending mysteries tied to cosmic dark matter halos, the vast, invisible cocoons that envelop galaxies and dictate their motion. From what these halos are made of and how they formed, to why they challenge our understanding of physics itself, we'll venture into questions that push the boundaries of imagination. You'll come away not only with a deeper appreciation of how much remains unknown, but with a sense of wonder at just how mysterious and magnificent our cosmos truly is. So settle in, we're about to pull back the curtain on the dark side of the universe. That invisible hand reveals itself most clearly in the grandest structures of all galaxies. To understand our first mystery, we must look at a galaxy not as a simple disk of stars, but as something far more complex. Think of a towering, intricate cathedral. What you see from the outside are the beautiful stained glass windows, the ornate stonework, the soaring spires. This is the luminous galaxy, the stars and gas we can observe. But what holds that entire magnificent structure upright? It's the hidden framework, the massive stone arches and deep foundations buried within the walls, unseen but absolutely essential. That is the dark matter halo. It's the gravitational foundation upon which the entire visible galaxy is built. This hidden architecture solves a very real and dramatic problem. When astronomers first measured the rotation speeds of stars and gas clouds within spiral galaxies, they expected something straightforward. Stars closer to the center, where most of the visible mass is concentrated, should orbit very quickly, much like Mercury zips around our sun. Stars farther out in the galactic suburbs, where mass is more spread out, should move much more slowly, just as Pluto takes its time on its distant, sluggish orbit. But that's not what they found, not at all. Instead, they discovered that stars at the very edge of a galaxy orbit at nearly the same incredible speed as those near the center. The entire galaxy rotates like a rigid plate, a solid disk. But according to the laws of gravity and everything we know about matter, a galaxy spinning that fast should have flung itself apart eons ago. The only possible explanation is that there is far more matter there than we can see. A tremendous amount of mass must be holding everything together with its gravitational pull. This matter forms a vast spherical halo that extends far beyond the galaxy's visible edge, its gravity governing the motion of everything within it. And this brings us to the core of the mystery. What is this stuff? We call it dark matter because it doesn't interact with light in any way. It doesn't glow like a star, it doesn't reflect light like a planet, and it doesn't block light like a cosmic dust cloud. It is completely and utterly transparent to the entire electromagnetic spectrum. This profound darkness tells us that dark matter isn't made of the same stuff as you and me. It isn't atoms, it isn't protons or neutrons. Those particles interact with light constantly. Dark matter must be something entirely different, a new type of particle that feels gravity, but is almost completely deaf to the other fundamental forces, especially the one responsible for light and electromagnetism. It's a ghostly substance that literally shapes the universe, yet passes through our world and even through us without a trace. But if dark matter forms this invisible foundation for every galaxy we see, then our own Milky Way should be no exception. It too must be embedded within a massive, spherical dark matter halo. And if our theories about how this mysterious substance behaves are correct, that halo shouldn't be a smooth, featureless cloud. Instead, the gravitational pull of the main halo should have captured countless smaller clumps of dark matter over billions of years, creating a swirling population of miniature subhalos. Each of these dense, invisible knots would act as a gravitational seed. According to our most sophisticated supercomputer simulations of cosmic evolution, a galaxy the size of the Milky Way should be surrounded by many thousands of these dark matter satellites. And here is where the plot thickens, because this prediction leads us directly to our second great mystery, the case of the missing galaxies. The logic seemed unassailable. Each of those dark matter subhalos has gravity, and gravity pulls in regular matter hydrogen and helium gas from the early universe. As the gas falls into a subhalo, it should compress, eventually becoming dense enough to spark star formation. Each successful subhalo should therefore give birth to its own tiny, dim galaxy, known as a dwarf satellite galaxy, destined to forever orbit the larger host like a moon around a planet. Our simulations confidently predicted that a typical Milky Way-sized dark matter halo should be attended by a vast entourage, a celestial swarm of thousands of these dwarf galaxies. Astronomers began searching the skies around our galaxy with this expectation, eager to map this predicted population, but the observations told a very different story. Instead of thousands, we have found only about 6 dozen dwarf galaxies orbiting the Milky Way. The numbers simply don't add up. It's as if we predicted a bustling metropolis based on the size of its power grid, but when we arrived, we found only a small, quiet village. This glaring mismatch between what our models predict and what our telescopes see is known as the missing satellites problem, and it has been a major headache for cosmologists for decades. So, where did everybody go? Scientists have been investigating two compelling and very different solutions to this cosmic whodunit. The first possibility is that our simulations are essentially correct, and the thousands of dark matter subhalos are indeed out there, but they are almost completely dark. In this scenario, the subhalos failed to form stars and became what are called dark galaxies. Why would that happen? The answer might lie in the very nature of star formation. For gas to collapse and form stars, it needs to cool down. But in the very smallest gravitational potential wells of these tiny subhalos, processes like supernova explosions or even the background ultraviolet light from the first stars in the early universe could have heated up or blown away the scant amounts of gas before it ever had a chance to form stars. These failed galaxies would be invisible to our telescopes, leaving only their silent, dark matter hearts orbiting in the darkness, forever undetectable by the light they emit. The second possibility is even more profound. It suggests our understanding of dark matter itself might be incomplete. Our current simulations are based on a leading model called cold dark matter, which assumes dark matter particles are slow-moving and only interact through gravity. But what if that's not the whole story? Some physicists propose alternative models, such as warm dark matter. In this idea, the dark matter particles would be lighter and faster moving in the early universe. This extra motion would have a smoothing effect, wiping out the smallest density fluctuations and preventing the very tiniest subhalos from ever forming in the first place. This would naturally result in far fewer satellite halos, bringing the predicted numbers much closer to the dozens of dwarf galaxies we actually observe. The missing satellites problem, therefore, isn't just a counting exercise. It's a critical test, forcing us to ask fundamental questions about the properties of the universe's most dominant yet elusive component. While the missing satellites problem had astronomers searching the skies for something that wasn't there, a third and even more contentious mystery was brewing, one that struck at the very heart of how we model dark matter's behavior. This controversy centers on a simple but crucial question: what is the precise shape of a dark matter halo's heart? For years, our most trusted supercomputer simulations, which model how dark matter clumps together under gravity alone, gave a very clear and consistent answer. They predicted that dark matter halos should have a specific density profile, meaning the amount of dark matter per cubic light year should follow a smooth mathematical curve, becoming incredibly dense at the very center of a galaxy. This model, known as the Navarro-Frenquite profile, describes a cusp, a sharp, steep rise in density right in the galactic core. Imagine a mountain with an impossibly sharp, pointed peak, so steep it's almost like a spike. According to the simulations, every galaxy's center should contain one of these dense dark matter spikes, a cusp. But when astronomers turned their telescopes to measure the actual mass distribution in real dwarf galaxies, the smallest and darkest galaxies, where dark matter dominates and should be easiest to study, they found something completely different. Instead of a sharp spike, the data suggested a much gentler, flatter distribution. It was more like a rounded hill than a treacherous peak. They called this a core. This wasn't just a minor discrepancy. It was a direct contradiction between our most fundamental theoretical predictions and hard observational evidence. The debate that followed, known as the cusp core problem, became one of the most heated in modern cosmology. It forced scientists to confront an uncomfortable possibility. Either our simulations of the universe's dominant ingredient were fundamentally flawed, or we were missing a critical piece of physics that could dramatically alter dark matter's behavior. One compelling solution to this puzzle doesn't require changing dark matter at all, but instead asks us to reconsider the power of the ordinary matter we can see. This explanation revolves around a process called baryonic feedback. Baryons is the scientific term for normal matter, protons, neutrons, and electrons, the stuff that makes up stars, planets, and us. For a long time, simulations focused purely on dark matter's gravity, treating regular matter as a passive bystander. But in reality, normal matter is capable of some truly violent and energetic acts. The idea is that over billions of years, the collective effect of exploding stars' supernova could have physically reshaped the dark matter halo itself. Here's how it might work. In the early universe, the first generations of massive stars form and then die in spectacular supernova explosions. These blasts generate enormous waves of energy, essentially creating powerful cosmic winds that push the surrounding gas out of the center of the dwarf galaxy. As this normal matter is ejected, the gravitational pull at the center suddenly decreases. Think of it like this: the dark matter particles are in a continuous orbit around the galactic center, their paths dictated by the combined gravity of both the dark matter and the ordinary matter. When a supernova blast violently kicks a huge amount of that ordinary matter outward, the central gravitational anchor is temporarily weakened. This causes the orbits of the dark matter particles to widen slightly, pulling them outward and effectively puffing up the center of the halo. If this cycle of star formation, explosion, and gas ejection happens repeatedly over cosmic time, these small kicks could add up, gradually smoothing out the predicted sharp cusp into the observed flat core. It's a fascinating idea because it suggests that the very thing dark matter ignores, the forces of electromagnetism and pressure that govern stars and gas, might, through gravity, leave an indelible imprint on dark matter's distribution. The other potential solution is more radical. It suggests that our basic assumption about dark matter only interacting via gravity might be wrong. What if dark matter particles can interact with each other through some unknown force, a dark sector version of electromagnetism? If these particles could collide or scatter off one another, it would introduce a form of internal pressure. In the dense, crowded environment of a galactic center, this self-interaction would act to smooth things out. Just as air molecules in a balloon bounce off each other to maintain an even pressure, self-interacting dark matter particles would redistribute their energy, effectively erasing the sharp density cusp and creating a soft core. This isn't a fringe idea. It's a serious field of study with specific models that make testable predictions, such as how dark matter halos of colliding galaxy clusters should behave. The cusp core problem, therefore, is more than a technical argument over density profiles. It is a direct experimental test, forcing us to choose between a universe where ordinary matter has a surprising gravitational influence on the dark cosmos, or a universe where dark matter itself is far more complex and interesting than we ever dreamed. Just when astronomers thought they had a handle on the missing satellites problem, an even more baffling puzzle emerged from the data, one that challenged not just the number of dwarf galaxies but their very nature. This fourth mystery is known as the too big to fail problem, and its name comes from a rather ironic twist of fate. During the 2008 financial crisis, the term was used for banks so large and interconnected that their failure was unthinkable. In our cosmic context, it refers to the most massive dark matter subhalos predicted by our simulations, halos so enormous and dense with gravitational potential that their failure to form bright, thriving galaxies seemed equally unthinkable. They were, in a cosmic sense, too big to fail, and yet the evidence suggests that is precisely what happened. Our most advanced cosmological simulations paint a very specific picture of these dominant subhalos. They are the heavyweight champions of the satellite population, the largest and most massive clumps of dark matter to be captured by a galaxy like our Milky Way. Their immense gravitational pull should have made them the most efficient star-forming factories in the galactic outskirts. We would expect each of these colossal subhalos to host a correspondingly massive and bright dwarf spheroidal galaxy, shining with the light of millions of stars. But when we look at the actual dwarf galaxies orbiting our Milky Way and our neighboring galaxy, Andromeda, the story is completely different. The most luminous dwarfs we see, like the Large Magellanic Cloud or Sagittarius, are indeed orbiting within substantial dark matter halos. But the simulations predict there should be even more of these giants, roughly 10 subhalos, that are significantly more massive than the ones hosting the dwarfs we know. These predicted behemoths are entirely missing from the observed lineup. It's as if we've found a few successful small businesses in a city, but the simulations tell us there should be a dozen corporate headquarters for Fortune 500 companies that are nowhere to be found. The heart of the problem lies in the internal properties of these unseen giants. Because they are so massive, the simulations show they should also be incredibly dense, especially at their centers. This density translates directly to gravity. A star orbiting within one of these predicted subhalos would be whipping around at an extremely high velocity, gripped by a powerful gravitational field. This is something astronomers can actually test. We can measure the velocities of stars within the dwarf galaxies we do observe. By tracking their motion, we can weigh the invisible dark matter halo holding them together. The results are startling. The dwarfs we see are all moving too slowly. Their stars are meandering along in relatively sedate orbits, indicating they are nestled within halos that have much lower central densities than the massive subhalos in the simulations. The predicted giants are not just missing. If they did exist with the densities forecasted, they would be impossible to hide. Their gravitational signature would be unmistakable, and the stars within them would be moving far faster than anything we've recorded. So where did these colossal halos go? Why did they fail to produce the bright galaxies we expect? Cosmologists have been exploring several fascinating avenues to solve this cosmic contradiction. One leading idea brings us back to the powerful influence of ordinary matter, but with a different twist. Perhaps these massive subhalos did indeed form, and they even began to collect gas and birth stars. But in these particularly dense environments, star formation might have been catastrophically intense. This isn't a gentle process. The first generation of stars would have been monstrously large, living fast and dying young in colossal supernova explosions. In a small, dense halo, these simultaneous blasts could have unleashed a fury of energy so extreme that it didn't just heat the gas. It blasted it all out into intergalactic space, permanently shutting down any future star formation. The subhalo would be left as a dark, starless ghost, its gravitational potential still immense but now completely invisible, explaining why our telescopes see nothing where our simulations predict a brilliant galaxy. Another possibility takes us back to the fundamental nature of dark matter, suggesting that the too big to fail problem and the cusp core problem might share a common solution. If dark matter is not completely cold and collisionless but instead has some capacity for interaction, this self-interaction could dramatically alter the internal structure of these massive halos. These particle collisions would transfer energy from the dense center out to the edges, effectively lowering the central density and making the core much softer and puffier. This process would transform a simulated subhalo from a dense, compact knot into a more spread out and diffuse cloud. The gravitational grip on its center would weaken, meaning any stars that did form would orbit more slowly, their velocities falling right in line with the sedate paces we actually observe in real dwarf galaxies. In this scenario, the massive subhalos haven't failed and they aren't missing. They are all around us, but they have been fundamentally reshaped by the intrinsic properties of dark matter itself. Their overachieving densities smoothed away into something more modest and in line with reality. This makes the too big to fail problem not just a puzzle about galaxy formation, but a potential key to unlocking the true physics of the universe's most mysterious substance. If dark matter provides the universal scaffolding for every galaxy, then you might expect a simple and predictable rule. A large dark matter halo gets a large galaxy, a small halo gets a small one. But the universe delights in chaos and complexity, and our fifth mystery shatters that simple expectation. We find that two dark matter halos, practically identical in mass and size, can host galaxies that are breathtakingly different from one another. One might become a magnificent star-forming spiral like our own Milky Way, with graceful arms winding through space. The other could evolve into a massive, red and dead elliptical galaxy, a vast and featureless sphere of ancient stars with no new birth and no discernible structure. This incredible diversity forces a profound question. If the gravitational foundation is the same, what other cosmic forces are at work in the architectural studio, deciding the final blueprint for a galaxy? To understand this, we need to look at a galaxy's entire life story, not just its final form. The initial conditions of a dark matter halo are indeed crucial: its mass, its spin, and how it grew over time through mergers with other halos. But these factors alone are not the sole authors of a galaxy's fate. They set the stage, but the play is acted out by the ordinary matter, the baryons, and their extraordinarily complex and often violent interactions. The journey from a primordial cloud of gas to a brilliant island of stars is a turbulent one, filled with feedback loops and competing processes that can push a galaxy down one evolutionary path or another. Consider the fate of gas, the raw fuel for star formation. In a forming halo, gas falls inward, drawn by the relentless pull of gravity. But what happens to that gas next is everything. In one scenario, the gas might settle into a calm, orderly rotating disk. As it cools gradually, it fragments into star-forming clouds, creating new generations of stars in a sustained and stable process. This is the path to a spiral galaxy, the dark matter halo's own angular momentum, a property inherited from the subtle tides of the early universe, can help foster this stable environment by encouraging the gas to spin in a coherent disk rather than collapsing into a chaotic mess. But this peaceful existence is not guaranteed. The alternative path is one of cosmic violence, a major merger. When two massive dark matter halos collide and merge, the galaxies living within them are thrown into gravitational chaos. Their delicate structures are utterly destroyed. The orderly motion of stars in disks is scrambled into random orbits, forming the smooth, puffed-up shape of an elliptical galaxy. Worse still, the immense gravitational forces of the collision can trigger a frenzy of star formation that rapidly consumes all the available gas, followed by the activation of a supermassive black hole at the galaxy's core. This black hole feasts on the surrounding turmoil, powering incredibly energetic jets that blast the remaining gas out of the galaxy entirely. This process, called quenching, effectively starves the galaxy of its future fuel, leaving it a red and dead relic filled with aging stars and incapable of making new ones. This explains why we see such a stark difference between galaxy types. A spiral galaxy is often the product of a relatively quiet, solitary life, patiently accreting gas and forming stars over billions of years. A giant elliptical is typically the product of a dramatic merger, a violent event that both triggers a final burst of stellar birth and then simultaneously shuts down the factory for good. The dark matter halo is the container, but the history of interactions within that container, the mergers, the black hole activity, the explosions of stars sculpts the final form. It's a powerful reminder that while dark matter builds the gravitational arena, the luminous matter within it writes its own dramatic and often destructive script. This remarkable consistency across the cosmos brings us to our sixth mystery, a puzzle that is perhaps the most elegant and perplexing of all. It turns out that despite the incredible diversity in their size and the wildly different galaxies they host, dark matter halos all share an identical internal blueprint. Whether it's a tiny halo weighing 1,000,000 times the mass of our Sun or a gargantuan one anchoring a massive cluster of galaxies a quadrillion times heavier, they all arrange themselves according to the same mathematical rule for their density. This universal preference for a single architectural plan, spanning 13 orders of magnitude in mass, suggests a profound and hidden order within the apparent chaos of cosmic structure. It's as if every single galaxy, from the smallest dwarf to the largest giant, was constructed using the exact same set of gravitational instructions. This universal blueprint is formally known as the Navarro-Frank-White profile, named after the cosmologists who first identified it in their landmark simulations. The profile describes a very specific pattern. The density of dark matter is incredibly high at the very center of the halo, and then it drops off in a predictable, smooth way as you move outward. The drop isn't linear, it follows a particular mathematical curve that seems to be nature's favorite shape for gravitational collapse. What makes this so astonishing is its sheer scale invariance. In physics, things that work for a single atom rarely work for a baseball, and systems that describe a baseball almost never apply to an entire planet. The forces at play, the physics involved, are completely different, but dark matter halos defy this expectation entirely. The same formula that describes the dark matter distribution in a puny dwarf galaxy also perfectly describes the halo of a magnificent spiral like the Milky Way, and even the immense halo of the Coma cluster, which contains thousands of galaxies. This is a span of mass so vast it's difficult to even comprehend, and yet one simple rule governs them all. So why does nature prefer this particular shape? Why is the NFW profile a universal constant for dark matter? the leading hypothesis points us back to the fundamental process of how these halos formed in the first place, through a mechanism known as hierarchical clustering. In the early universe, dark matter was not smoothly distributed. Instead, it had tiny, random fluctuations. Some regions were ever so slightly denser than others. Over billions of years, gravity acted on these minute differences. The denser patches had more gravity, so they pulled in more material from their surroundings, growing even denser. This process continued in a cascade, with small halos forming first and then merging together to build larger and larger structures. It's a violent history of collisions and cannibalism on a cosmic scale. The remarkable finding from simulations is that this specific process of growth through accretion and merger seems to naturally erase the memory of a halo's initial conditions and its violent formation history. No matter how many mergers it underwent, no matter what size it started as, the end result of this gravitational mixing and relaxation is always the same stable configuration, the NFW profile. It appears to be an attractor state in the language of physics, a stable endpoint that all halos inevitably evolve toward through the relentless action of gravity. It is the most efficient, the most stable, and therefore the most natural way for a large collection of collisionless particles to arrange themselves under their own gravitational influence. This universality is both a blessing and a curse for cosmologists. It's a blessing because it provides a stunningly simple rulebook. If you know the total mass of a dark matter halo, you can confidently predict the density of dark matter at any point within it, from its heart to its outer edge. This makes modeling the universe infinitely easier, but it's also a curse because this very simplicity hides the underlying physics. The NFW profile emerges from simulations that use the simplest possible assumptions about dark matter, that its particles are cold or slow-moving, and that they only interact through gravity. The fact that this simple model so accurately replicates the observed large-scale structure of the universe is the primary reason the cold dark matter model has been so dominant. It works beautifully right up until it runs into those smaller scale problems like the missing satellites and the cusp core crisis. This creates a fascinating tension. The universal success of the NFW profile on large scales is the strongest evidence we have for the cold dark matter model. Yet, its potential failure on the smallest scales, in the hearts of dwarf galaxies, might be the very clue that leads us to a richer, more complex theory. It forces us to ask if the profile is truly universal, or if our observations of small galaxies are revealing a subtle break in the pattern, a break that could open a window into the true nature of the dark universe. The profile is not just a description, it is a deep question written in gravity, asking us to figure out why it holds such sway over the cosmos. But if the dark matter halo is the essential foundation for building a galaxy, what happens when that foundation is laid but the construction crew never arrives? This brings us to our seventh mystery, the haunting possibility of halos without galaxies, vast, invisible structures of pure dark matter that drift through the cosmic void like ghost ships, completely empty and undetectable by the light they emit. The idea of these failed galaxies is a direct and inevitable prediction of our cosmological models. In the grand hierarchy of structure formation, the smallest dark matter halos are the first to condense out of the primordial universe. The problem is, many of these early halos are simply too tiny to hang onto their gas. Their gravitational pull is so weak that any internal event, like the heat from the first stars, or even the background radiation from the Big Bang itself, can easily prevent gas from cooling and collapsing, or even blow it away entirely. Without gas, there can be no stars, and without stars, the halo remains forever dark, a silent monument to a galaxy that never was. The quest to find these invisible halos is one of the most creative and challenging endeavors in modern astronomy. Since they emit no light, we cannot see them directly. Instead, we have to infer their presence by watching how they bend the very fabric of reality itself through gravity. One of the most promising techniques is gravitational lensing, a phenomenon predicted by Einstein where a massive object acts like a cosmic lens, warping the space around it and magnifying or distorting the light from objects far behind it. Normally, we use this to study massive galaxy clusters, but to find isolated dark halos, astronomers have to become far more subtle detectives. They employ a method called quasar microlensing. By continuously monitoring the flickering light of a distant quasar, a brilliantly luminous active galaxy, they can look for telltale, short-lived changes in its brightness. If an invisible, massive object like a pure dark matter halo happens to drift directly between us and the quasar, its gravity will briefly focus the quasar's light, causing a tiny but detectable flash. It's like watching a distant street lamp through a swirling fog, waiting for an unseen figure to pass in front of it and momentarily change its glow. Another ingenious method involves looking for the impact these dark halos might have on the things we can see. Imagine a visible dwarf galaxy, a small collection of stars orbiting our Milky Way. If a pure dark matter halo were to pass through or very near this dwarf galaxy, its gravitational pull would tug on the stars, perturbing their smooth orbital flow. This would leave a distinct fingerprint in the motion of the stars, a kind of gravitational wake that could, in theory, be detected through precise measurements. While this is incredibly difficult to do, it represents another way we might one day catch a dark halo in the act of revealing itself through its silent influence on the luminous world. The hunt for these phantoms is more than a theoretical exercise, it is a critical test. Finding a population of pure dark matter halos would be a tremendous victory for the standard cold dark matter model, confirming its prediction that the universe should be filled with these dark foundations. Their absence, however, would be just as telling, forcing us to radically reconsider our understanding of how structure forms in the dark cosmos. But this elegant picture of a universal dark matter blueprint leads us to a surprisingly practical and deeply philosophical eighth mystery. Where does a dark matter halo actually end? We might picture these halos as neat, spherical objects with a clear boundary, like a soap bubble floating in space, but the reality is far messier and more fascinating. Determining the true edge of a dark matter halo is one of cosmology's trickiest boundary disputes because a halo isn't a solid object with a surface. It's a gradual fading of density against the background of the universe. There is no signpost out in the void that reads, "You are now leaving the Milky Way's dark matter halo." So, how do we define the edge of something that has no hard edge? Scientists have developed several clever definitions, each useful for a different purpose, but none providing a single, absolute answer. The most common definition is based on a concept from the early universe called the background density. Imagine the cosmos has a baseline density of matter, a faint, nearly uniform mist of particles spread throughout space. A dark matter halo is a region where the density has condensed to become significantly higher than this universal average. Cosmologists often define the edge of a halo as the radius where its density falls to exactly 200 times the average density of the universe. This value, while seemingly arbitrary, is chosen because it aligns with the theoretical point where a collapsing cloud of matter first breaks away from the overall expansion of the universe and becomes a distinct gravitationally bound object. It gives us a standardized, if theoretical, way to compare the sizes of different halos. Another critical definition is the virial radius. This concept comes from the idea of virialization, the state where a gravitational system has settled into a stable, balanced configuration. Within this radius, the particles, be they stars or dark matter, are orbiting in a way that is balanced and self-contained, having shaken off the memory of their recent chaotic formation. Beyond this point, matter is still falling in for the first time. It hasn't yet been assimilated into the relaxed, swirling population of the inner halo. The virial radius essentially marks the boundary between the halo's settled population and the cosmic newcomers still arriving. Yet even this is a statistical boundary, not a physical wall. Perhaps the most intuitive way to think about a halo's edge is through its gravitational influence. After all, gravity does not simply stop. It weakens with distance but never truly vanishes. The Sun's gravity holds Pluto in orbit even at a staggering distance, and the Milky Way's gravitational reach extends even beyond its visible satellite galaxies. So, we could define the edge as the point where the halo's gravitational pull is no longer the dominant force acting on an object, where the tidal forces from a neighboring galaxy or the overall expansion of the universe finally take over. This makes the boundary not only fuzzy but also dynamic, changing over time as galaxies move and interact. A star or a stream of gas can be right at the precipice, caught in a delicate tug of war between the gravitational pull of its home halo and the vast attractive forces of the cosmic structures around it. This ambiguity has real consequences for how we measure the universe. When we cite the mass of a galaxy cluster or the size of the Milky Way's halo, the number is entirely dependent on which definition of the edge we choose. A calculation based on the 200 times density threshold will give one mass, while a measurement that includes all matter still gravitationally influenced might give a much larger one. This boundary problem means that the fundamental properties we assign to the largest structures in the cosmos, their mass, size, and even their very existence as isolated objects, are ultimately approximations based on the definition we find most useful. It's a profound reminder that our clean, categorical maps of the universe are often overlays on a reality that is far more continuous, interconnected, and beautifully indistinct. This invisible boundary dispute over where a halo truly ends leads us to consider the most massive and powerful objects that can form deep within them, supermassive black holes. At the heart of nearly every large galaxy, including our own Milky Way, lies one of these cosmic behemoths, weighing in at millions or even billions of times the mass of our Sun. Their existence poses our ninth great mystery. What is the hidden relationship between a dark matter halo and the monstrous black hole at its center? Is the black hole merely a passive resident, or does it play an active role in shaping the very halo that hosts it? This is a cosmic chicken and egg problem that gets to the very heart of how structure forms in the universe. For a long time, astronomers viewed these two entities as separate components of a galaxy. The dark matter halo forms the vast, overarching gravitational framework, while the supermassive black hole is a much later development, a tiny but incredibly dense knot of ordinary matter that collapsed in the very center. Their size difference is almost incomprehensible. A typical dark matter halo can span hundreds of thousands of light years. A supermassive black hole's event horizon, the point of no return, would be smaller than our solar system. It would be like comparing the entire continent of North America to a single grain of sand. Yet, despite this staggering difference in scale, a surprising and powerful correlation has been discovered. The mass of a galaxy's central supermassive black hole is directly proportional to the mass of its entire dark matter halo. The bigger the halo, the bigger the black hole. This connection is too precise to be a coincidence, suggesting that the formation and growth of these two utterly different objects are fundamentally intertwined from the very beginning. This correlation forces us to ask a critical question: which one is in the driver's seat? Does the dark matter halo control the growth of the black hole, or does the black hole somehow regulate the entire halo? The leading explanation, known as the bottom-up scenario, gives the dark matter halo the primary role. In this view, the initial conditions are set by the halo's formation. The size, mass, and gravity of the collapsing dark matter cloud determine how much gas can fall into the center of the budding galaxy. A more massive halo pulls in more gas, creating a denser, richer central reservoir. This abundant fuel supply does two things. First, it allows for the rapid formation of a massive central bulge of stars. Second, it provides a vast amount of food for the nascent black hole to feast upon, enabling it to grow to a correspondingly enormous size. In this model, the black hole mass and the stellar bulge mass are both consequences of the underlying dark matter halo's gravity. The halo calls the shots, and the black hole simply grows to match the size of its gravitational home. However, there is a competing and far more active hypothesis. This top-down scenario suggests that the black hole is not a passive passenger but a powerful engine that can fundamentally influence its entire host. This idea centers on the concept of feedback. When a supermassive black hole is actively feeding, it doesn't do so quietly. The infalling matter releases a phenomenal amount of energy, powering luminous quasars and blasting out jets of radiation and particles at near light speed. This outpouring of energy can heat the surrounding gas, preventing it from cooling and falling in to form new stars. In the most extreme cases, it can even drive powerful winds that blow huge quantities of gas completely out of the galaxy. This process, known as AGN or active galactic nucleus feedback, doesn't just shut down star formation, it may also alter the distribution of dark matter itself. By ejecting a significant amount of normal matter from the galactic center, the black hole effectively weakens the gravitational anchor at the core. This could, over billions of years, cause the dark matter particles to shift to wider orbits, potentially helping to transform a predicted dense cusp into a more observed soft core. In this dramatic narrative, the tiny black hole becomes the master of its domain, using tremendous bursts of energy to put the brakes on its own growth while simultaneously sculpting the invisible dark matter architecture that surrounds it. Unraveling this mystery is one of the key goals of modern astrophysics. It requires piecing together the life history of galaxies from their birth in the early universe to the present day. Observatories like the James Webb Space Telescope are peering back in time to catch galaxies and their central black holes in their infancy, hoping to see which came first, the growth of the halo or the ignition of the black hole. Meanwhile, sophisticated computer simulations are now trying to model both dark matter and the complex physics of black hole feedback simultaneously. The answer is likely a complex dance, a feedback loop where the halo sets the stage, but the black hole becomes a powerful actor that can rewrite parts of the script. Understanding this intricate relationship is crucial because it doesn't just affect a single galaxy. The energy released by these feasting black holes can heat the intergalactic medium for millions of light years around, influencing the formation of entire galaxy clusters and governing the rate at which the cosmic star-forming factories eventually shut down. The story of a dark matter halo and its central black hole is a story of gravitational destiny and energetic rebellion, a partnership that shapes the visible universe. If the dark matter halo provides the gravitational blueprint for a galaxy, then the timing of its construction is everything, setting the stage for all that follows. This brings us to our 10th mystery, a question of cosmic chronology. Why did some dark matter halos form astonishingly early, mere moments after the Big Bang in cosmic terms, while others assembled at a much more leisurely pace over billions of years? This isn't just a question about dates on a cosmic calendar. It's about understanding the initial conditions of the universe itself and how the tiniest of seeds grew into the vast structures we see today. The story of halo formation begins with the primordial universe, a hot, dense soup of particles and energy. At this time, dark matter was not perfectly smooth. Thanks to quantum fluctuations that were stretched to cosmic scales during a period of rapid expansion called inflation, some regions were ever so slightly denser than others. These minute-over densities were the seeds of all future structure. Gravity is an amplifier, it loves inequality. A slightly denser patch has slightly more gravity, which pulls in more dark matter from its surroundings, making it even denser. This runaway process over billions of years is what built the cosmic web of dark matter halos we see today. but the rate of this growth was not uniform across the universe. The timing for any given halo depended on two key factors: the initial size of its seed and its location in the cosmic landscape. Imagine two patches of the early universe. One patch had a particularly large and pronounced overdensity, a grand mountain in the making. The other patch had a much smaller, more modest fluctuation, a gentle hill. The large overdensity had a head start. Its stronger gravitational pull allowed it to overcome the expansion of the universe more quickly, collapsing into a bound, virialized dark matter halo far earlier than its smaller counterpart. The smallest halos of all, with masses perhaps only 1,000,000 times that of our Sun, are predicted to have formed first when the universe was less than 100 million years old. Meanwhile, the average halo that would one day host a galaxy like our Milky Way took much longer to assemble, its growth happening through a hierarchical process of mergers and accretion over billions of years. But the initial size of the seed wasn't the only factor. Location was equally critical. A small overdensity that had the incredible luck to form in an already dense environment, a future galaxy cluster in the making, would find itself surrounded by a rich reservoir of dark matter to draw from. It would be like a sapling planted in fertile, well-watered soil, growing rapidly by consuming the abundance around it. Conversely, a similarly sized seed that formed in an underdense region, a future cosmic void, would be starved for material. Its growth would be stunted, taking far longer to reach maturity, like a plant struggling in a desert. This means the entire history of a dark matter halo, when it formed, how quickly it grew, and how massive it eventually became, was dictated by the lottery of its initial conditions, the size of its primordial fluctuation, and the density of its neighborhood. The implications of this formation timeline are profound, especially for the galaxy that eventually forms within the halo. An early forming halo has a tremendous advantage. It begins pulling in vast quantities of pristine hydrogen and helium gas from the surrounding intergalactic medium long before most other structures. This gives it first pick of the universe's resources, allowing it to build a massive galaxy very quickly. We see evidence of this in the existence of incredibly massive, bright galaxies that astronomers have spotted at very high redshifts, meaning they existed when the universe was only a few 100 million years old. These cosmic behemoths, which theories struggle to explain, must have been built within exceptionally early forming and rapidly growing dark matter halos that enjoyed the most privileged starting conditions imaginable. On the other hand, a late-forming halo has a very different destiny. By the time it finally gathers enough mass to start pulling in gas efficiently, the universe has changed. The intergalactic medium is no longer pristine. It has been polluted by heavy elements from the first generations of stars and heated by the intense radiation from quasars and galaxies. This processed gas is harder to cool and collapse, making star formation a slower, less efficient process. Furthermore, a galaxy born late in a less dense environment may never experience a major merger, dooming it to a quiet life as a small, faint dwarf galaxy or a humble spiral, never achieving the grandeur of the early forming giants. The timing of the dark matter halo's assembly doesn't just influence the galaxy's size, but its very type, its stellar population, and its entire evolutionary history, a legacy written in gravity during the universe's first fleeting moments. Yet for all its gravitational might, a dark matter halo seems to be a terribly inefficient manager of its most valuable resource, the ordinary matter, the atoms that are supposed to form the stars and planets of the galaxy within it. This brings us to our 11th mystery, a problem that hits closer to home than any other because it's about the very stuff we're made of. Cosmologists can calculate with remarkable precision how much normal matter, also known as baryonic matter, should exist in the universe based on observations of the cosmic microwave background, the afterglow of the Big Bang. This gives us a universal budget for atoms, We then look at the mass of a dark matter halo, which we can measure from its gravity, and we expect the amount of baryons inside it to be a specific fraction of that total mass, reflecting that universal ratio. But when we add up all the visible components of a galaxy, the stars, the glowing gas, the planets, we come up dramatically short. A huge portion of the baryons are simply missing. For a galaxy like the Milky Way, we've only found about half of the atoms that our theories say should be there. In smaller dwarf galaxies, the situation is even worse, with over 90% of their expected ordinary matter unaccounted for. So where did it all go? This is the missing baryons problem, and solving it means tracing the epic journey of matter in and out of the gravitational wells of dark matter. The leading theory is that these atoms aren't truly missing. They were never truly and permanently ours to begin with. The story begins with the dark matter halo acting as a powerful gravitational trap. In the early universe, it pulls in vast amounts of primordial hydrogen and helium gas from the intergalactic medium. For a time, this gas collapses, cools, and begins to form the first stars. But this is where the peaceful process of accretion turns violent. Those first stars are anything but gentle. They are massive, hot, and short-lived, ending their lives in titanic supernova explosions. Each explosion does more than just create heavy elements. It floods the nascent galaxy with energy, heating the surrounding gas and driving powerful winds. In a small dwarf galaxy with a relatively weak gravitational pull, these winds can be catastrophic. They can blow huge quantities of gas right out of the halo and back into intergalactic space, permanently stripping the galaxy of its future fuel supply. This is likely why many dwarf galaxies have so few stars and why they seem to have lost almost all their baryons. They were essentially stillborn, their potential snuffed out by the very first generations of stars. But what about larger galaxies like our own? Their gravity is much stronger, making it harder for gas to completely escape. Here, the plot involves a more complex cycle of ejection and recycling. Supernova, and even more powerfully, the activity of the central supermassive black hole can heat gas to immense temperatures. Instead of being blown completely away, this gas is pushed out into the galaxy's extended halo, forming a vast, hot atmosphere known as the circumgalactic medium. Imagine a galaxy not as an island in an empty sea, but as the active core of an immense hot cloud. This cloud is the reservoir for the missing baryons. The gas in this halo is so hot millions of degrees that it doesn't emit visible light. It glows faintly in high-energy X-rays, making it incredibly difficult to detect. From this reservoir, some gas might eventually cool and fall back into the galaxy in a process called recycling, fueling new rounds of star formation. But a significant portion of it may remain suspended in this hot state for billions of years, effectively hidden from our view but still gravitationally bound to the halo. We are, in a sense, living in the heart of a giant, invisible cloud of our own galaxy's exiled material. There is another, even more expansive possibility for the missing atoms. Some baryons may have been blown so far out by galactic winds that they escaped the halo's grip entirely, rejoining the general intergalactic medium. This warm hot gas that filaments the cosmic web between galaxies could account for a significant portion of the universal budget of baryons that seems to be missing from individual galaxies. This means the atoms aren't lost, they've just been redistributed from the dense concentrations within halos to a more diffuse, universe-wide presence. Finding this diffuse material is one of the great observational challenges in astronomy, requiring sensitive telescopes tuned to specific ultraviolet and X-ray wavelengths to detect the extremely faint emission or absorption signatures of this incredibly sparse gas. The missing baryons problem ultimately forces us to change our perspective. A galaxy is not a closed system. It is a dynamic engine, constantly breathing in and out, accreting material from the cosmos and expelling it back out through powerful feedback processes. The story of a galaxy is not just about what it manages to keep, but also about what it has lost. This incredible evidence for dark matter's existence comes from the most violent events in the universe, the collisions of entire galaxy clusters. These cosmic crashes are the largest and most energetic events since the Big Bang itself, and they provide a unique and powerful laboratory for studying the properties of dark matter directly. The most famous and decisive of these collisions is the Bullet Cluster, a system of two galaxy clusters that have recently smashed right through each other at staggering speeds. By studying the aftermath, astronomers were able to do something astonishing. They effectively took a picture of dark matter, not by seeing it, but by mapping its gravitational shadow. The results were both a triumph for the dark matter hypothesis and the source of our 12th great mystery, revealing new and puzzling behaviors in the process. To understand what makes the Bullet Cluster so special, we need to think about what happens in a collision between two such massive objects. Each cluster is made of three main components: hundreds of galaxies themselves, huge clouds of hot gas that fill the space between those galaxies, and an immense, overarching dark matter halo that holds everything together. When two clusters collide, these three components behave in completely different ways. The individual galaxies are like swarms of bees. They are mostly empty space, so when two swarms pass through each other, the chances of any two bees actually hitting each other are incredibly small. The galaxies simply pass right through, largely unaffected by the collision, carried along by the overall motion of their parent halos. The hot gas between the galaxies, however, is a different story. This gas is a diffuse but tangible substance, and it behaves more like a fluid. When the two clusters collide, the clouds of gas from each one slam into each other. This creates a tremendous shock wave, much like the sonic boom from a jet fighter, which heats the gas to even more incredible temperatures and causes it to glow brightly in X-rays. Crucially, this intergalactic gas experiences a powerful drag force. It gets slowed down and stuck in the center of the collision, but the dark matter is the real key. According to the prevailing cold dark matter model, dark matter particles should behave almost like the galaxies. They are thought to interact only through gravity, not through any other force. This means they should feel no friction, no pressure, and no drag. Just like the swarms of galaxies, two clouds of dark matter should simply pass right through each other without slowing down. This is exactly what observations of the Bullet Cluster revealed, and it was a landmark moment in science. Astronomers used a technique called gravitational lensing to map the total mass distribution in the colliding clusters. By measuring how the cluster's gravity warps the light from more distant galaxies behind it, they could create a map of where the mass is concentrated. They then used X-ray telescopes to map the location of the hot, colliding gas. The results were stunning and clear. The total mass, the dark matter, was not in the same place as the hot gas. The two dark matter halos had indeed passed through the collision and were now located on either side of the central impact zone, precisely where the galaxies were also located. The hot gas, however, was lagging far behind, stuck in the middle. The dark matter had become completely separated from most of the normal baryonic matter. This observation was a direct and spectacular confirmation of the dark matter hypothesis. It proved that most of the matter in the clusters is indeed dark, and it behaves exactly as predicted. It feels gravity but no other forces, allowing it to sail through a colossal collision unscathed. It effectively ruled out alternative theories of gravity that sought to explain galactic rotation without dark matter, as those theories would not have allowed for such a clean separation between the mass and the visible matter. Yet, this very success also opened a new box of puzzles, raising questions about the finer details of dark matter's nature. While the overall behavior confirmed the model, subsequent studies of other cluster collisions have revealed some intriguing and less straightforward results. In a few systems, the dark matter appears to be lagging behind its galaxies slightly, or the separation isn't as clean as in the bullet cluster. This has led some scientists to ask a profound question. Is dark matter truly as non-interacting as we think? Could there be a very, very weak force that allows dark matter particles to interact with each other just a tiny bit? This possibility is known as the self-interacting dark matter model. The idea is that dark matter particles might occasionally bounce off each other, creating a faint internal friction. In most situations, this effect would be negligible, but in the extreme environment of a high-speed cluster collision, this tiny amount of friction could cause the dark matter cloud to slow down ever so slightly, creating a small but measurable offset from the position of the completely collisionless galaxies. It's a subtle effect, but modern gravitational lensing techniques are becoming sensitive enough to potentially detect it. The bullet cluster itself actually places tight constraints on how strong this interaction could be, but it doesn't rule it out entirely. Other cluster collisions are now being intensely studied to see if they show evidence for this faint drag, which would be the first hint of a rich, dark sector of physics operating entirely hidden from our view. These colossal collisions are more than just cosmic accidents. They are fundamental experiments. They allow us to test the properties of dark matter in a way we never could in a laboratory on Earth. Each new cluster merger discovered adds a new data point, helping us to understand whether dark matter is perfectly simple and collisionless, or if it possesses a hidden complexity that only reveals itself in the most violent and extreme conditions the universe can provide. The bullet cluster gave us our first clear glimpse of the dark universe, and the clusters that follow are now challenging us to see even deeper into its secrets. While the idea of a universal density profile suggests a deep underlying order, the actual forms these halos take are anything but uniform. In the grand tapestry of the cosmos, no two dark matter halos are exactly alike. Some are almost perfectly spherical, serene and symmetrical cocoons of shadow. Others are wildly elongated, stretched into cosmic footballs or even triaxial ellipsoids, looking as though they've been pulled in 3 different directions at once. This astonishing diversity in shape is our 13th mystery, and it tells a story of violent origins and chaotic growth, a narrative written not in light but in the silent geometry of gravity. So what determines whether a halo ends up round like a ball or flat like a disk? The answer lies almost entirely in its unique and violent assembly history. A dark matter halo is not born in a single event. It is built over billions of years through a relentless process of mergers and acquisitions. Smaller halos are constantly being drawn in by gravity, colliding with and being absorbed by the larger structure. The final shape of the halo is essentially the sculpted remnant of all these collisions, a fossil record of its growth. Think of it like working with a ball of clay. If you simply add more clay evenly from all sides, you'll maintain a spherical shape. But if you repeatedly slam other lumps of clay into it from one specific direction, you'll end up with an elongated, distorted form. This is precisely how a dark matter halo evolves. The most significant factor in determining a halo's shape is the timing and direction of its last major merger. A halo that has recently experienced a massive collision, where it absorbed another large halo of comparable size, will be highly disturbed. The incredible gravitational forces involved in such an event can stretch the entire structure, pulling it into a distinctly elongated shape. This is a temporary state of cosmic chaos. Over time, through a process called violent relaxation, the particles will settle into a new, stable configuration. But the memory of that violent impact is often preserved in the halo's final, non-spherical form. Conversely, a halo that has lived a relatively quiet life for the last several billion years, growing only by slowly accreting a smooth rain of matter from its surroundings or by consuming only very small halos, will have had time to settle into a much more relaxed and spherical state. Its history has been calm and its shape reflects that peace, but mergers aren't the only force at work. Another critical ingredient is a property known as spin. Just as planets spin on their axes and galaxies rotate, dark matter halos also possess a net angular momentum, a slow, collective rotation imparted by the tidal torques of neighboring structures in the early universe. This spin has a fascinating effect on the halo's shape. As the halo rotates, centrifugal force pushes dark matter particles outward, but only in the directions perpendicular to the axis of spin. This causes the halo to flatten slightly, much like a pizza chef spinning dough to form a flat, wide disc. A halo with a high spin will therefore be more oblate, flattened at the poles, than one with very little rotation. In the most extreme cases, this can create a halo that is almost to sky, though never as flat as the visible disk of a spiral galaxy, because the dark matter particles, lacking any friction, cannot lose energy and settle into such a thin plane. The environment a halo lives in also plays a crucial role in sculpting its form. A halo that resides in a dense region, like a burgeoning galaxy cluster, is constantly being tugged and pulled by the gravitational forces of its numerous neighbors. These persistent tidal forces can stretch a halo, pulling it out of shape and often aligning its longest axis in the direction of the greatest pull, like iron filings aligning with a magnetic field. A halo floating in an isolated cosmic void, free from such external harassment, is much more likely to retain a symmetrical, spherical shape, its form dictated solely by its own internal dynamics. This diversity is more than just a curiosity, it is a powerful tool for astronomers. By studying the shapes of dark matter halos through techniques like gravitational lensing, we can essentially read their life stories. A spherical halo whispers a history of quiet, steady growth. A highly elongated one shouts about a recent, dramatic merger. This allows us to test our models of cosmic structure formation in a new way. Our most sophisticated simulations successfully reproduce this wide variety of shapes, giving us confidence that we understand the basic physics at play. Yet they also present new, subtle challenges. For instance, the relationship between a halo's spin and its shape isn't always as straightforward as the pizza dough analogy suggests, hinting that there may still be more physics to uncover in the dark sector. The varied forms of these invisible giants are a direct window into the dynamic and often violent processes that have shaped the universe from its earliest moments to the present day. Just as the varied shapes of dark matter halos tell their own violent stories, their silent, steady rotation adds another layer of intrigue to the cosmic narrative. This brings us to our 14th mystery, the unexpected and specific spin of these invisible giants. We often picture galaxies as magnificent spinning pinwheels, but we rarely stop to consider that the vast, invisible halos surrounding them are also rotating, their gravitational foundations imbued with a deep, slow momentum of their own. The question of how they acquired this spin, and why it seems to be so intimately connected to the fate of the visible galaxy within, opens a fascinating window into the dynamics of cosmic structure. The story of a halo spin begins not with a single event, but with the subtle gravitational tides of the early universe. In the primordial cosmos, dark matter wasn't perfectly smooth, it was a web of tiny density fluctuations. As these fluctuations began to collapse under their own gravity to form the first halos, they didn't exist in isolation. Each budding proto-halo was surrounded by neighbors, each exerting a slight gravitational pull. It is this network of external tugs that provides the torque. Imagine two dancers starting to move around each other. Their gravitational attraction doesn't just pull them together, it also imparts a spin to their system. On a cosmic scale, as dark matter flows inward along the filaments of the cosmic web, these tidal torques from surrounding structures set the entire collapsing cloud into a slow, steady rotation. This process imprints a specific amount of angular momentum onto the halo, a kind of cosmic birthright that depends entirely on the initial arrangement of matter in its vicinity. This inherited spin is not random. Our most sophisticated simulations show a remarkable consistency, predicting that dark matter halos should have a specific, relatively narrow range of spin parameters, a mathematical description of their rotation rate. It seems the universe has a preferred setting for how fast these gravitational structures turn. But this prediction leads to a profound and still unanswered question: why this particular value? The answer may lie in the efficiency of the tidal torque process itself and the subsequent history of mergers. A halo that forms from a smooth, steady accretion of matter tends to have a lower spin, while one that has undergone a major merger can have its angular momentum significantly altered, often increased. The final spin is a fossil record, a number that encodes the halo's entire assembly history. The most captivating part of this mystery, however, is the connection between the spin of the invisible halo and the rotation of the luminous galaxy it hosts. There is a compelling correlation. Halos that spin faster tend to host galaxies with disks that also rotate more rapidly. This makes intuitive sense. The gas that falls into a halo to form the galaxy carries with it the angular momentum of the halo itself. As the gas collapses further to form the disk, conservation of angular momentum forces it to spin faster, much like an ice skater pulling their arms in to accelerate a spin. The dark matter halo provides the initial impetus, the foundational momentum that the visible galaxy then amplifies into the brilliant, spinning disks we observe. Yet, this relationship is not a perfect one-to-one mapping, and the differences are where the real physics lies. The process is incredibly efficient, but not perfectly so. Some of the halo's original angular momentum can be lost by the gas through various mechanisms during the complex journey of galaxy formation. Turbulence, magnetic fields, and most importantly, feedback from supernova and active black holes can transfer angular momentum away from the collapsing gas, effectively applying a brake to the system. This can explain why some galaxies with high spin halos might have slower than expected rotation, or why the size of a galactic disk is ultimately limited. The final rotation rate of the stars we see is a delicate balance between the initial spin gifted by the dark matter and the subsequent astrophysical processes that can either preserve or dissipate that precious momentum. It's a cosmic dance where the invisible partner leads, but the visible one can sometimes stumble, its steps complicated by the fiery processes of its own creation. This intricate dance of spin and structure finds its grandest expression in the largest architecture of the universe, a vast and magnificent network known as the cosmic web. This brings us to our 15th mystery, a question that shifts our perspective from individual galaxies to the entire universe. What is the fundamental relationship between dark matter halos and the cosmic web? Do the halos form first at the intersections of these cosmic filaments, acting as anchor points, or does the web itself emerge from the connections between halos? Understanding this is key to mapping the flow of matter along the universe's largest highways. To picture the cosmic web, imagine the universe on its grandest scale. It is not a random scatter of galaxies like seeds tossed onto soil. Instead, it is a highly structured, web-like network of massive filaments or strands connecting immense, dense galaxy clusters at the nodes. Between these brilliant structures stretch vast, empty cosmic voids, deserts of near-nothingness that can span hundreds of millions of light-years. This entire breathtaking structure is woven from dark matter. It is the gravitational skeleton upon which the visible universe is built, and dark matter halos are the dense knots within that skeleton. The formation of this web is a direct result of the initial conditions set after the Big Bang. Those tiny quantum fluctuations in the primordial density of dark matter were not random dots. They formed a specific pattern of ripples. As gravity began to work over billions of years, it amplified these ripples in a predictable way. The slightly denser regions collapsed into flat sheets and long filaments, while the under-dense regions expanded into voids. The points where multiple filaments crossed became the sites of the most extreme gravitational collapse, the natural places for the largest and most massive dark matter halos to form. In this top-down view, the cosmic web defines the playing field, and the halos are the players that emerge at the most advantageous positions on the board. However, there is also a powerful bottom-up perspective. While the web provides the initial blueprint, the halos themselves become active agents in shaping it. As a halo grows at a node, its immense gravitational pull begins to draw matter not just from its immediate surroundings, but from far along the filaments connected to it. These filaments act as cosmic highways, funneling a steady stream of gas and even smaller dark matter halos toward the waiting giant at the intersection. The halo's growth reinforces the filament, making it a more prominent and efficient conduit. It's a symbiotic relationship. The web dictates where the halos form, and the halos, in turn, strengthen and define the web through their gravitational influence. This flow of matter is a continuous process that is still happening today. We can observe its effects by studying the motion of galaxies. Galaxies within the dense clusters at the nodes move on rapid, random orbits. But galaxies located within the filaments themselves are often caught in a more orderly flow, streaming along these dark matter rivers toward the gravitational attractors at the ends. This constant accretion is how the largest structures in the universe, galaxy clusters, continue to gain mass, growing even larger by feeding on the cosmic currents that connect them to the rest of the web. The cosmic web is not a static sculpture, it is a dynamic, evolving system. In the early universe, the web was finer and more numerous, with a greater density of small filaments feeding a vast number of growing protogalaxies. Over time, through the relentless pull of gravity, the cosmic web undergoes a process of simplification and reinforcement. Smaller filaments merge to form thicker ones, and smaller halos merge to form larger ones. The web coarsens, with the most prominent filaments becoming the enduring superhighways of the cosmos, draining matter from the smaller tributaries and feeding the most massive clusters. Studying the detailed structure of this web, the thickness of its filaments, the distribution of its nodes, and the emptiness of its voids provides astronomers with a powerful test for our cosmological models, offering a unique window into the strength of gravity and the very properties of dark matter itself. These ancient, colossal halos present a timeline that seems almost impossibly tight, pushing our models of cosmic evolution to their very limits. The core of the issue is a matter of sheer growth against the relentless expansion of the universe. In the standard model of structure formation, gravity needs time to work. It must first overcome the outward momentum of the Big Bang's expansion to pull matter together, then orchestrate a complex hierarchy of mergers to build something truly massive. For a halo containing the mass of a massive galaxy cluster to form, conventional wisdom suggested this process should take billions of years. Yet, the evidence from telescopes like James Webb is showing us that these giants were already in place when the universe was a mere 5% of its current age. It's the cosmic equivalent of finding a fully grown redwood tree in a forest of saplings that are only a few years old. The question isn't just how it got there, but what extraordinary conditions allowed it to grow so astonishingly fast. This premature maturation forces us to re-examine the very first moments of the universe and the initial seeds from which all structure grew. The leading theory points a finger at the period of inflation, a fraction of a second after the Big Bang when the universe expanded at an exponential rate. During this violent expansion, quantum fluctuations were stretched to macroscopic sizes, creating the primordial density variations that would later become the gravitational seeds for galaxies and clusters. The ancient halo problem suggests that the pattern of these initial fluctuations might not have been perfectly uniform. Perhaps there were rare, exceptionally large peaks in the primordial density field, cosmic lottery winners that started off with a tremendous head start. These overdensities were so pronounced that they began collapsing practically immediately. their immense gravity allowing them to rapidly draw in matter from their vast surroundings, essentially shortcutting the slower, hierarchical merger process that built most other structures. The properties of dark matter itself are under scrutiny in this mystery. The rapid formation of these ancient behemoths places stringent constraints on how dark matter must behave. For instance, a model involving warm dark matter, where particles are lighter and faster moving, would have a natural smoothing effect that suppresses the formation of the very smallest structures. This would actually make it harder to form enormous halos so early, as there would be fewer building blocks available for rapid assembly. The existence of these ancient halos therefore lends strong, albeit indirect, support to the cold dark matter model, where slow-moving particles can clump together efficiently from the very beginning. However, it also demands that the model operate at peak efficiency in these rare, overdense environments of the early cosmic web. Beyond the initial conditions, the location of these halos was everything. A massive seed is necessary, but it is not sufficient. It also needs a rich and abundant source of fuel to feed its growth. In the early universe, the densest regions were the intersections of the nascent cosmic web, the future nodes where filaments of dark matter crossed. A proto-halo forming at this privileged crossroads had access to a veritable superhighway of matter, with dense flows of dark matter and gas funneling into it from multiple directions simultaneously. This rapid, focused accretion allowed it to grow at a breathtaking pace, essentially gorging itself on the surrounding material while other regions were still taking their first tentative steps toward collapse. The ancient halo problem isn't just about the halos themselves, but about recognizing that the universe from its very inception was a place of extreme inequality, where the luck of the draw in location and initial density could create incomprehensible giants in the blink of a cosmic eye. But if the ancient halo problem shows us the incredible power of gravity to build structure, our 17th mystery introduces a force working in direct opposition, a force that could ultimately unravel everything gravity has built. We now turn to the most enigmatic relationship in all of cosmology, the interplay between the dark matter halos that pull the universe together and dark energy, which is relentlessly pushing it apart. For billions of years, gravity has been the undisputed architect of the cosmos, sculpting dark matter into halos, galaxies, and the vast cosmic web. But observations in the late 1990s revealed a shocking truth. The universe's expansion is not slowing down due to gravity's pull, as everyone expected. It is accelerating, driven by a mysterious repulsive force we call dark energy. This discovery sets the stage for a cosmic tug of war on the grandest possible scale, a battle that will determine the ultimate fate of all structure in the universe. So how does this accelerating expansion affect the dark matter halos that form the backbone of everything we see? The immediate effect is a dramatic change in the environmental conditions for growth. For most of cosmic history, a dark matter halo acted like a gravitational pit, pulling in matter from its surroundings. It grew by accreting smaller halos and drawing in streams of gas and dark matter along the filaments of the cosmic web. But dark energy alters this landscape profoundly. As the expansion of space accelerates, the distance between galaxies and clusters increases at a faster and faster rate. The cosmic web, the very highway system that feeds the growth of halos, begins to stretch and fray. The filaments connecting structures become longer, thinner, and more tenuous. The steady flow of matter into a waiting halo doesn't just slow down, it can be completely severed. A halo that once enjoyed a rich diet of incoming material finds itself on a cosmic island, isolated and starved of the resources it needs to continue growing. This leads to a fascinating and well-established concept in cosmology known as halo mass quenching. In the current dark energy-dominated era, there is a theoretical maximum size that a dark matter halo can achieve. Once the expansion rate surpasses a critical threshold, the gravitational pull of a halo can no longer overcome the stretching of space to capture new material from beyond its immediate vicinity. Its growth stagnates. It has reached its final mass. The largest galaxy clusters we see today are likely these maximum mass halos. They are the ultimate products of gravitational assembly in our universe, cosmic dinosaurs that will never grow larger than they are right now. Their evolution is effectively frozen, their future one of slow decline rather than continued growth, but the long-term implications are even more radical and sobering. The current acceleration is not just a one-time event. If dark energy behaves as the simplest model suggests, as a constant force inherent to the fabric of space itself, known as a cosmological constant, then its repulsive power will only grow stronger as the universe expands and becomes emptier. This raises a terrifying possibility for the distant future, trillions of years from now. Could dark energy eventually overcome gravity's hold not just on intergalactic scales, but within individual halos themselves? Could a galaxy or even a star system be torn apart from the inside by the expansion of the universe? For now, and for a very long time to come, the answer is a resounding no. Within a gravitationally bound system like a galaxy, a star cluster, or our own solar system, the force of gravity is immensely stronger than the minuscule pull of dark energy. The space within our Milky Way is not expanding, the solar system is not getting larger, and the Earth is not being slowly pulled away from the Sun. Dark energy's effect is only noticeable in the vast, empty voids between galaxies where gravity's grip is weak. However, in a far, far future where dark energy's influence has grown exponentially, some models suggest that even the most tightly bound systems may not be safe. On timescales so long they defy comprehension, the relentless acceleration could, in theory, become so powerful that it overwhelms the gravitational bonds holding galaxies, stars, and even atoms together. This hypothetical endgame is known as the Big Rip scenario. While the Big Rip remains a speculative possibility dependent on the exact, unknown properties of dark energy, the more immediate and certain reality is that dark energy has already begun to dictate the future of cosmic large-scale structure. It has thrown a switch in the universe's evolution, moving us from an era of construction to an era of isolation and eventual dissolution. The great age of galaxy and cluster building is coming to an end. The dark matter halos that have been the engines of creation for 13 billion years are now facing a future where their influence wanes, and the silent, repulsive force of dark energy becomes the dominant voice in the cosmos, writing a final chapter of solitude and stillness. And now we come to a mystery that hits remarkably close to home, a puzzle written in the motion of our own galactic neighbors. For decades, our best cosmological simulations have portrayed the dark matter halo of a large galaxy like our Milky Way as a roughly spherical cloud, a gravitational nest from which we would expect a swarm of satellite dwarf galaxies to orbit in a chaotic, random, three-dimensional ballet. Their path should be a jumble of inclinations and directions, a reflection of the halo's own overall shape. But when astronomers began to meticulously map the orbits of the dwarf galaxies surrounding us and our nearest large neighbor, Andromeda, they discovered something that sent a shockwave through the field. These satellites are not moving randomly at all. Instead, they are aligned in startlingly thin, vast, and coherently rotating planes of motion. It's as if we expected a chaotic swarm of bees, but instead found a precise, structured squadron of aircraft flying in formation. This is the satellite plane mystery, and it stands as one of the most persistent and direct challenges to our simplest models of dark matter and cosmic structure. The most famous of these structures is the vast polar structure around our own Milky Way. Several of its key satellite galaxies, including the majestic Large and Small Magellanic Clouds, are not just randomly placed, they are arranged along a single, immense plane that slices through the galactic poles. Even more intriguingly, many of these satellites share a common direction of motion, suggesting they are not just statically aligned but are dynamically linked, orbiting together within this thin disk. The situation around the Andromeda Galaxy is, if anything, even more pronounced. Observations have revealed that a significant fraction of its satellite galaxies are locked into an extremely thin, rotating plane, a structure so vast and flat it defies easy explanation within the standard model. These are not minor alignments, they are major architectural features of our local galactic group, and they appear to be a common, if not universal, phenomenon. This creates a profound tension with our cosmological simulations. In the cold dark matter model, structure forms hierarchically, with large halos growing by consuming hundreds of smaller ones. These accreted subhalos, which host the dwarf galaxies, are expected to be delivered from all directions, their orbits preserving the random, chaotic paths of their infall. A computer simulation of a Milky Way-like galaxy will indeed produce a population of satellite galaxies, but they are invariably distributed in a much puffier, more spherical configuration. Their orbits are random, with no preference for a single, shared plane or a common direction of rotation. The fact that we observe such stark, thin planes in reality, while our best theoretical models consistently fail to produce them, suggests a critical piece of physics is missing from our equations. It's a discrepancy that cannot be easily dismissed, pointing either to a flaw in our understanding of dark matter itself or a gap in our knowledge of how galaxies form within these halos. Scientists have been exploring several compelling and hotly debated solutions to this cosmic conundrum. One line of thinking suggests the answer lies not with dark matter, but with the ancient history of the galaxies involved. This is the ancient filament hypothesis. Recall that galaxies form along the dense filaments of the cosmic web. It's possible that the dwarf galaxies we see today in a plane around the Milky Way or Andromeda did not arrive individually, but were all once part of a single, colossal filament of gas and dark matter that was feeding the growth of the central galaxy billions of years ago. As this filament was drawn in, the dwarf galaxies within it, like beads on a string, would have inherited its preferred direction. Their orbits would remain correlated in a single plane, a fossilized memory of their shared origin in that primordial cosmic highway. This is an elegant solution that uses the known large-scale structure of the universe to explain the alignment, but it requires the filament to be exceptionally long-lived and coherent to have delivered so many satellites in such a precise configuration. Another fascinating possibility involves the dynamic interplay between the satellites themselves. Could the plane be a temporary structure, a cosmic coincidence that will eventually dissolve? This seems unlikely given the number of satellites involved and the fact that we see similar structures around both major galaxies in our local group. However, some researchers have investigated whether the gravitational influence of the largest satellites, like the Large Magellanic Cloud, could be shepherding smaller dwarfs into a common plane over time. While this can influence a few objects, it is generally considered insufficient to orchestrate the entire, vast satellite population into the thin, rotating structures we observe. The most radical explanations point back to the nature of dark matter. Could the satellite plane mystery be another clue, like the cusp core problem, that dark matter is not perfectly cold and collisionless? Some alternative models, particularly those involving self-interacting dark matter or warm dark matter, can affect how subhalos fall into a larger galaxy and how their orbits evolve over time. If dark matter particles can interact even very weakly, it could cause a form of dynamical friction that preferentially aligns orbits or makes them more susceptible to staying within a disk-like distribution. While these models are still being developed and tested, the existence of these planes provides a critical observational benchmark that any successful theory of dark matter must now be able to explain. The satellites are not just orbiting, they are sending us a message, and we are only just beginning to understand what it is they are trying to say about the true nature of the dark universe that surrounds us. To understand the grand architecture of dark matter halos, we must rewind the clock to the very beginning, to a fleeting moment of unimaginable energy that set the entire cosmic drama in motion. The story of these invisible giants is not written solely by gravity's relentless pull over billions of years. Its opening lines were scribed in the first trillionth of a second after the Big Bang, during a period known as cosmic inflation. This was a time when the universe expanded at a rate so exponential it defies all analogy, stretching a subatomic volume of space to a size larger than our observable universe today. During this incredible burst of growth, the universe was not perfectly smooth. Thanks to the bizarre rules of quantum mechanics, empty space itself was fizzing with tiny, temporary fluctuations, particles, and energy popping in and out of existence. As inflation stretched the fabric of space-time, it also stretched these quantum fluctuations, locking them in and magnifying them from the microscopic to the cosmic scale. These minute ripples in the density of the universe became the primordial seeds for all structure to come. The slightly denser regions would, over billions of years, become the gravitational wells that pulled in dark matter to form the first halos. The pattern of these ripples, imprinted across the entire sky, was the initial blueprint, the cosmic lottery that determined where the great clusters, the vast filaments, and the immense voids would one day form. The incredible precision of this process is what makes the connection so profound. The initial conditions set by inflation weren't random. They followed a specific statistical pattern predicted by quantum physics. These fluctuations are known to be nearly scale invariant, meaning they were roughly the same amplitude regardless of their size. This is why we see dark matter halos following that universal density profile across such a staggering range of masses, from the tiniest dwarfs to the largest clusters. They all grew from the same type of seed, just on different scales. The entire cosmic web, with its halos at the nodes and filaments connecting them, is essentially a three-dimensional fossil of those quantum fluctuations, magnified to an astronomical scale. We can even see this primordial blueprint directly in the cosmic microwave background, the oldest light in the universe. The tiny temperature variations in this afterglow map are direct photographs of those density fluctuations, the slightly hotter spots showing the regions that were slightly denser, the very spots that would eventually collapse into the first dark matter halos. It's a breathtaking link between the quantum world and the galactic, a direct line from the uncertain flicker of particles in a vacuum to the majestic swirl of a galaxy. This deep connection allows cosmologists to use the large-scale structure of the universe, the distribution and properties of dark matter halos, as a powerful test for theories of inflation itself. By meticulously measuring the clustering of galaxies and the masses of halos across space, we are effectively reading the statistics of those initial quantum ripples. The specific way halos are distributed, how they cluster together, and the ratio of massive halos to smaller ones all serve as a diagnostic tool. For instance, the details of this clustering can tell us about the energy scale at which inflation occurred, a fundamental parameter that remains otherwise inaccessible. If we were to discover that the number of very ancient massive halos is different from what the simplest inflationary models predict, it could point us toward more complex physics operating during that first explosive moment. In this way, the dark matter halos we study today are not just the end product of cosmic evolution. They are also messengers from the universe's birth, carrying encoded information about the physics of the very first instant of time, a permanent record of the quantum origin of all structure. This remarkable consistency in the blueprint of individual halos finds its parallel on the grandest scale of all, in the sheer number of them. Across the entire observable universe, from our local cosmic neighborhood to the most distant regions we can peer into, the population of dark matter halos follows an incredibly strict and predictable census. This is the universal halo mass function, and its unwavering regularity is a silent testament to the powerful, simple rules that govern the birth and growth of all structure. It tells us that while the fate of any single halo might be a chaotic story of mergers and chance, the collective destiny of trillions upon trillions of them is governed by a profound statistical order. Imagine you could take a colossal inventory of the entire cosmos, counting every single dark matter halo and carefully sorting them by mass. What you would find is a distribution that is far from even. The universe is overwhelmingly populated by tiny, lightweight halos. These are the cosmic equivalents of small towns and villages, vastly outnumbering everything else. As you move up the mass scale to the halos that host galaxies like our Milky Way, the great metropolitan centers of the universe, they become significantly more rare. And at the very top of the scale, the halos that anchor immense galaxy clusters, the true cosmic megalopolises, are the rarest of all. They are the ultimate prizes in the gravitational lottery. This pattern isn't just a snapshot of today. If you could go back in time and take the same census, you would find that this same general shape holds true. The overall number of halos increases as the universe ages and gravity has more time to work, but the ratio remains strikingly consistent. The small always outnumber the large, following a specific mathematical curve that our theories can predict with astonishing accuracy. This predictability is a direct consequence of the initial conditions imprinted by inflation. The quantum fluctuations that were stretched to cosmic scales had a very specific statistical character. They were nearly scale invariant. This means that the amplitude of a density fluctuation was roughly the same, regardless of whether it was destined to become a tiny halo or a giant one. There were simply far more small fluctuations than large ones. Gravity then acted as a relentless amplifier on this initial pattern. A region that started off only slightly denser than average would collapse into a small halo relatively quickly. A region that was exceptionally overdense was incredibly rare, but it would eventually grow into one of the massive cluster halos. The halo mass function we see today is therefore a direct reflection of that initial lottery ticket handed out in the first instant of time. It is the final outcome of gravity acting for 13.8 billion years on a very specific set of starting rules. This makes the halo mass function one of the most powerful tools in a cosmologist's toolkit. It serves as a critical bridge between the primordial universe and the cosmos we observe today. By measuring the number of galaxy clusters in a given volume of space, astronomers can work backwards to constrain the exact parameters of our cosmological model. The abundance of the most massive clusters is exquisitely sensitive to both the overall density of matter in the universe and the exact nature of those initial inflation-born fluctuations. Finding a cluster that is too massive for its time can challenge our entire understanding of structure formation, as we saw with the ancient halo problem. Conversely, confirming that the cluster count matches predictions is a huge victory for the Standard Model. It's a way of using the largest gravitationally bound objects in the universe to test the physics of the smallest conceivable scales. The unwavering nature of this cosmic census also places tight constraints on the properties of dark matter itself. Alternative models like warm dark matter predict a very different mass function. By suppressing the formation of the smallest halos, a WDM universe would have a noticeable lack of cosmic villages, shifting the entire distribution toward more medium-sized halos. The fact that our observations of dwarf galaxies and gravitational lensing continue to support a universe filled with an abundance of low-mass halos is strong evidence in favor of the cold dark matter paradigm. The halo mass function is not just a description of what's out there, it is a fundamental test, and so far, the simplest version of our theory has passed with remarkable marks. It reveals a universe that, for all its apparent complexity and chaos, operates on a set of elegant and statistically predictable principles, from the vastest cluster to the most humble dark matter clump. But what if we've been reading the cosmic map all wrong? What if the invisible hand shaping galaxies isn't an unseen substance at all, but a fundamental misunderstanding of the force itself? This brings us to our 21st mystery, a radical alternative that challenges the very core of our cosmic detective story. The possibility that dark matter halos are not physical objects, but ghostly illusions created by gravity itself behaving in ways we never anticipated. This is the world of modified Newtonian dynamics, or MOND, a theory that proposes there is no dark matter, only a subtle tweak to the laws of gravity that becomes apparent in the vast, feeble gravitational fields of galaxies. The motivation for MOND is born from a desire for simplicity and a deep-seated unease with the dark matter paradigm. For decades, we have been inferring the existence of an invisible, unknown substance to explain the gravitational anomalies we see. To a MOND proponent, this feels like adding an endless series of epicycles to explain the motion of planets before the Copernican revolution revealed a simpler solar system. Their proposal is elegantly straightforward. Instead of inventing a new form of matter, perhaps Isaac Newton's famous law of universal gravitation is simply incomplete. Newtonian gravity works perfectly within our solar system, but what if it breaks down at the incredibly low accelerations found in the outer reaches of galaxies? MOND suggests that below a certain critical acceleration threshold, gravity stops fading with the square of the distance and instead transitions to a new regime, becoming stronger than Newton or Einstein predicted. This extra gravitational kick would then explain why stars at the edges of galaxies orbit so quickly, making the need for a dark matter halo completely unnecessary. The initial appeal of MOND was its stunning success in a specific arena. It could beautifully reproduce the rotation curves of a wide variety of spiral galaxies with a single new constant, something that the dark matter model struggled with at the time without finely tuning each individual halo. It wasn't just a vague idea, it was a specific mathematical formula that made a clear prediction. For many, this was a powerful Occam's razor argument. Why invoke a vast, complex, and unseen universe of particles when a simple modification to a well-known law could do the trick? However, the true test of any scientific theory is not how well it explains the data it was designed for, but how it holds up against new and different evidence. This is where MOND faces its most serious challenges. While it can excel at explaining the internal dynamics of individual galaxies, it struggles catastrophically with the largest scales of the universe. The most damning evidence comes from observations of colliding galaxy clusters like the Bullet Cluster. Remember, in these cosmic crashes, we see a clear separation between the bulk of the mass, mapped by gravitational lensing, and the visible matter, seen in X-rays. The dark matter model explains this perfectly. The collisionless dark matter halos pass through each other, while the gaseous plasma gets stuck in the middle. MOND, however, has a profound problem here. Its modification is tied to the acceleration of individual stars within a galaxy. In the wide open spaces between galaxies in a cluster, the accelerations are too high for MOND's effects to kick in, meaning it should not provide any extra gravitational force. The theory predicts that the lensing map should perfectly follow the visible mass, the hot X-ray gas, but the data shows the exact opposite. The gravity is where the gas is not. For many, this single observation is a near-fatal blow to pure MOND, as it appears to require that some form of unseen matter is still present, effectively reintroducing the very thing it sought to eliminate. The challenges don't end there. The precise pattern of fluctuations in the cosmic microwave background, the ancient light from the Big Bang, is exquisitely sensitive to the composition of the universe. The observed peaks and troughs in this radiation can only be explained if the universe contains about 5 times more matter than exists in atoms. This is a cornerstone of the standard cosmological model and is completely independent of galaxy rotation curves. To accommodate this, MOND would need to be integrated into a full relativistic theory, a task that has proven immensely difficult. While there are efforts to create such a framework like TVS tensor vector scalar gravity, these models often become more complex and contrived than the dark matter they aim to replace, requiring their own additional fields and parameters, arguably losing the elegant simplicity that was MOND's original appeal. Furthermore, the theory has a hard time explaining the broad range of halo properties we've explored throughout this video. The universal halo mass function, the correlation between a black hole's mass and its halo, and the detailed gravitational lensing by isolated galaxies all point toward the presence of a separate, collisionless component of matter that can cluster independently of the stars and gas. MOND effectively attributes the missing mass to the location of the visible matter, making it difficult to explain why the gravitational effects don't always perfectly align with the light. The debate between dark matter and modified gravity is often framed as a battle, but in reality, it has been incredibly productive for science. MOND has acted as a fierce and intelligent competitor, forcing dark matter theorists to sharpen their models and make more precise, testable predictions. It has pushed the entire field to find better evidence, like the bullet cluster, that can distinguish between the two ideas. While the vast majority of cosmologists now believe the evidence overwhelmingly supports the existence of a dark matter particle, the persistence of MOND reminds us that science must always entertain alternative explanations. It stands as a testament to the fact that our understanding of gravity, one of the most fundamental forces in the universe, may still have surprises in store, and that the final chapter on the dark matter halo mystery may yet contain a twist that none of us see coming. Yet for all the profound regularity of the halo mass function, the universe has a way of ensuring that no two halos, even those of identical weight, ever have exactly the same story to tell. This brings us to our 22nd mystery, a subtle but powerful cosmic bias that reveals how a halo's history is just as important as its mass. We've grown accustomed to thinking that a dark matter halo's role in the cosmos is defined by a single number, its mass. A 10 trillion solar mass halo should behave a certain way, live in a certain environment, and host a certain type of galaxy regardless of its past. But this clean, simple picture is being upended by a phenomenon known as assembly bias. This is the startling discovery that two halos with precisely the same mass can have wildly different clustering properties, meaning they congregate with other halos in different ways based entirely on when and how they formed. It's a finding that challenges the very idea of mass as a cosmic destiny, introducing a rich new layer of complexity to the dark matter narrative. To understand assembly bias, imagine two corporations that have the exact same market valuation today. On paper, they are identical in size and financial power, but one company is a centuries-old legacy institution that grew slowly and steadily through careful reinvestment and organic growth. The other is a disruptive tech startup that achieved the same valuation through a frenzied series of mergers and acquisitions, absorbing smaller companies in a rapid, aggressive expansion. Despite their identical net worth today, their corporate cultures, their risk profiles, and their future prospects are entirely different. The same is true for dark matter halos. A halo that assembled its mass early in the universe's history, in a rapid, violent burst of mergers, will have a different personality, a different relationship with its cosmic environment than a halo of the same mass that built itself gradually and peacefully over a much longer period. This difference in personality manifests most clearly in how these halos socialize. Astronomers measure this by looking at their clustering, which is essentially a measure of how likely a halo is to have close neighbors. The surprising finding is that, for a given mass, halos that formed earlier are significantly more likely to be found in dense regions, clustered tightly together with other halos in the bustling metropolises of the cosmic web. Their older, more established nature makes them gravitate toward the dense centers. Meanwhile, halos of the same mass that formed later are more often found in the cosmic suburbs or even the isolated countryside, preferring a more solitary existence. Their formation history has left them on the outskirts. This is the essence of assembly bias. Your past determines your present address, even if your current bank account is the same as your neighbor's. Why would this happen? The answer lies in the dynamic nature of the cosmic web itself. The universe is not a static stage, it's a constantly evolving landscape. In the early universe, the densest regions were the first to collapse and form halos. A halo that managed to form early in one of these dense knots was already in the right place at the right time. It was born into a rich neighborhood and naturally grew up surrounded by other halos. Furthermore, the very process of early, rapid assembly often involves major mergers, which can dramatically alter a halo's internal structure, making it more concentrated and dense. This higher concentration makes it more resilient to tidal forces, allowing it to survive and even thrive in the crowded, violent environment of a galaxy cluster. On the other hand, a late-forming halo has a very different origin story. It might have started life in a moderately dense region that took much longer to collapse, or it might have grown by slowly accreting matter in a quieter part of the universe. This leisurely pace means it avoided the dramatic mergers that characterize early formation. Without that violent history, it likely has a lower concentration, a more relaxed internal structure. When such a halo eventually finds itself drawn into a dense cluster by the large-scale pull of gravity, it is more vulnerable. The tidal forces from its massive neighbors can strip away its outer layers, potentially inhibiting its growth and preventing it from ever becoming a dominant central galaxy. It remains a satellite, forever influenced by its more established peers. The discovery of assembly bias forces a significant shift in our understanding of galaxy formation. For decades, the primary focus was on connecting a galaxy's properties, its size, its shape, its star formation rate, to the mass of its dark matter halo. This was the core of the galaxy-halo connection. Assembly bias tells us this picture is incomplete. It's not just how much dark matter you have, but how you got it that shapes your destiny. Two galaxies residing in halos of identical mass could look completely different because one halo assembled early and the other late. The early forming halo, born in a dense environment, might have had its gas supply shock heated by the surrounding cluster, quenching its star formation and turning it into a red and dead elliptical galaxy. The late-forming halo, growing in isolation, might have held onto its gas and formed a beautiful, star-forming spiral disk. Their dark matter foundations weigh the same, but the galaxies they host are worlds apart. This revelation means that to truly understand a galaxy, we must become cosmic archaeologists. We need to dig into the history of its dark matter halo, uncovering its formation timeline and merger tree. Modern cosmological simulations are now powerful enough to track this information for millions of virtual halos, allowing us to quantify the strength of assembly bias and its impact on the visible universe. Observers, in turn, are looking for signatures of this bias in large galaxy surveys, trying to see if galaxies with older stellar populations, a sign of an early forming halo, are indeed more strongly clustered than galaxies with younger stars but the same mass. This intricate interplay between a halo's mass, its formation history, and its environment adds a beautiful layer of complexity to the cosmic story, reminding us that in the grand tapestry of the universe, every thread has a unique and influential past. This incredible interplay between a halo's history and its cosmic address sets the stage for one of the most transformative periods in all of cosmic history, a time when the first dark matter halos did more than just build galaxies, they fundamentally altered the nature of the entire universe. This brings us to our 23rd mystery, a pivotal era known as the Epoch of Reionization. a cosmic dawn where the first light from the first halos sparked a revolution that changed the cosmos forever, a process in which these halos were both the architects and the subjects of a vast and sweeping upheaval. For hundreds of millions of years after the Big Bang, the universe was a profoundly dark and simple place. It was filled with a dense, neutral fog of primordial hydrogen gas, a featureless sea that absorbed any light trying to pass through it. The only source of illumination was the fading afterglow of the Big Bang itself, the cosmic microwave background, shifting into longer, invisible wavelengths as the universe expanded. This period is aptly named the Cosmic Dark Ages, but this neutral fog could not last forever. Its fate was sealed the moment the very first dark matter halos reached a critical mass, their gravity finally strong enough to collapse the first pockets of gas and ignite the very first stars. These first luminous objects, known as Population 3 stars, were unlike anything that exists today. They were behemoths, hundreds of times more massive than our Sun, burning ferociously hot and brilliant, and living short, violent lives. The light these first stars emitted was not like the gentle sunshine we know. Their surface temperatures were so extreme that they blazed with intense, high-energy ultraviolet photons. And this specific type of radiation possesses a unique and powerful property. It has enough energy to rip electrons away from the neutral hydrogen atoms that filled the universe. This process, called ionization, is what gives the epoch its name. Each photon from these first stars could strike a neutral hydrogen atom and break it apart into a free-flying electron and a proton, effectively burning away the cosmic fog and creating vast, growing bubbles of transparent, ionized plasma. This was the dawn of reionization, the moment the universe switched from being opaque and neutral to transparent and ionized, a state it has maintained ever since. But this was not a gentle sunrise. It was a chaotic and patchy process, a cosmic firestorm spreading unevenly through the cosmos, and its progress was dictated entirely by the distribution and growth of those first dark matter halos. The role of dark matter halos in this cosmic drama was absolutely fundamental. They were the essential gravitational engines without which reionization could never have begun. The very first stars, and later the first galaxies and quasars, could only form at the centers of these halos, where gravity had won its first victories over the expansion of the universe. The rate and the pattern of reionization were therefore a direct map of where these halos were forming and how quickly they were growing. The process likely started slowly around the densest, most massive halos that formed earliest. Each of these halos, hosting a brilliant first star or a small cluster of them, became a lone lighthouse in a vast, dark ocean, its UV radiation carving out a small, isolated bubble of ionized gas in the neutral fog. As time went on, more and more halos reached the critical mass needed to form stars, and these individual bubbles began to grow and overlap like rising yeast cells in a cosmic loaf of bread, eventually merging into vast ionized regions. However, this story is not a simple one-way street where halos influence reionization without consequence. The feedback from this process was immediate and brutal, and it dramatically affected the halos themselves, particularly the smallest ones. The same ultraviolet radiation that was ionizing the cosmic fog was also a destructive force for star formation in the smallest dark matter halos. Here's why: for a small halo to form stars, it needs to pull in neutral hydrogen gas and allow that gas to cool and collapse. But the intense UV background radiation created by the first generation of stars made this incredibly difficult. When a high-energy photon hits a hydrogen atom, it doesn't just ionize it, it also heats the surrounding gas. This heating raises the pressure, making it harder for the gas to compress. Even worse, this pervasive radiation field made it nearly impossible for molecular hydrogen to form. Molecular hydrogen was the primary coolant for these first pockets of gas. Without it, the gas couldn't lose its heat and condense into stars. This created a fascinating cosmic feedback loop. The largest halos, with their deep gravitational wells, were relatively immune to this effect. Their strong gravity could overcome the increased gas pressure and continue to pull in and collapse gas, allowing them to form more and more stars and become the dominant sources of ionizing radiation. But for the legions of smaller halos, the dawn of reionization was a catastrophe. Just as they were on the verge of forming their own first stars, the universe around them was flooded with radiation that effectively sterilized them. Their gas was heated and prevented from cooling, permanently stifling their ability to form stars. This process, known as radiative feedback, is a leading explanation for the missing satellites problem we explored earlier. The thousands of small dark matter subhalos predicted by theory may have failed to form galaxies not because they didn't exist, but because their star-forming potential was extinguished by the very first starlight that illuminated the cosmos. The reionization epoch, driven by the largest halos, may have set the final population of visible dwarf galaxies we see today, favoring the survival of the biggest and suppressing the smallest. The timing and the completion of this epoch are therefore a critical puzzle. Observations of the most distant quasars and the cosmic microwave background tell us that the universe was fully reionized by the time it was about 1 billion years old. But pinning down exactly how it started and how long it took is an active area of research, with major observatories like the James Webb Space Telescope peering back to this very era. By finding the earliest galaxies and measuring their ionizing output, we can finally understand the detailed choreography between the growth of the first dark matter halos and the great cosmic awakening they triggered. The epoch of reionization was not just a switch being flipped, it was a complex, evolving battle between gravity's power to build and light's power to destroy, a battle that shaped the future of galaxy formation and left an indelible mark on the universe we observe today. Given the relentless tug of war between gravity and dark energy, the ultimate fate of a dark matter halo is a story written over timescales that dwarf the current age of the universe. For the foreseeable future, measured in tens of billions of years, the halos that have already achieved virialization, a stable, balanced state, will remain largely intact. Their internal gravitational bonds are far too powerful for the expansive force of dark energy to break. Stars will continue to orbit within their galaxies, and galaxies will continue to circle within their host halos, all held firmly in place by the immense, invisible mass at their core. Yet, while their internal structure remains secure, their growth is another matter entirely. The era of dramatic expansion is over. As the universe's acceleration continues, the supply lines of the cosmic web are being stretched and severed. The steady rain of fresh dark matter and intergalactic gas that once fed these halos will slow to a trickle and then stop completely. Each halo, from the smallest dwarf to the largest galaxy cluster, will eventually reach its final maximum mass, becoming a closed and isolated gravitational island in the expanding void. This isolation, however, is not a peaceful stasis. Over truly astronomical timescales, the universe becomes a place of profound and silent change. The primary mode of evolution for these halos shifts from growth to a slow, inevitable erosion through a process known as dynamical relaxation. Within a halo, dark matter particles and stars are in constant, chaotic motion. Over countless orbits, these motions lead to a phenomenon called two-body relaxation, where gravitational interactions between particles gradually exchange energy. This has a smoothing effect, but it can also, over eons, lead to the evaporation of the outermost material. Particles on the most extended orbits can gain just enough energy from encounters to be flung out of the halo entirely, escaping its gravitational grip and joining the general background of the universe. It's an incredibly slow leak, a process that operates on timescales far longer than the current age of the universe, but given enough time, it can cause a halo to very gradually lose mass and become slightly more compact. The most dramatic fate is reserved for halos that are not isolated, but are instead satellites of larger structures. For a dwarf galaxy halo orbiting a massive host like the Milky Way, the future is one of gradual dissolution. With each pass, the immense tidal forces from the central galaxy pull and stretch the smaller halo, stripping away its outer layers of dark matter and stars. This tidal stripping can be so effective that over many orbits, a satellite halo can be completely torn apart. Its constituent particles are then assimilated into the larger halo's diffuse outer region, or they may be cast out into intergalactic space. The visible signature of this process is the beautiful but tragic stellar stream we see today, like the streams emanating from the Sagittarius dwarf galaxy, which are the ghostly remnants of a halo that is being systematically devoured. This is the hierarchical model in reverse, not growth through mergers, but a slow gravitational decomposition where the largest halos consume the smallest. But the true endgame, the final chapter for all dark matter halos, hinges entirely on the unknown nature of dark energy. If dark energy is a constant cosmological constant, as current evidence suggests, then the fate we've described, eternal isolation and slow evaporation, is the most likely outcome. The acceleration will continue, driving all other galaxy clusters beyond our cosmological horizon and leaving our local group as an isolated island universe. However, there are more speculative and far more violent possibilities. Some theories propose that dark energy is not constant but evolves over time, a concept known as quintessence. In one terrifying scenario, the strength of dark energy could increase exponentially, becoming so powerful that it overwhelms not just the expansion of the universe, but every fundamental force. This is the Big Rip. In this model, the repulsive force would eventually become strong enough to tear apart galaxy clusters, then individual galaxies, then solar systems, and finally, in the last moments, atoms and subatomic particles themselves. In this apocalyptic finale, even the mighty gravitational bonds within a dark matter halo would be instantly and utterly vaporized, shredding the cosmic architecture into its fundamental components. While considered unlikely, the Big Rip remains a stark reminder that the ultimate destiny of everything, even the invisible scaffolding of the cosmos, is inextricably tied to the mysterious and dominant force of dark energy. And so we arrive at the final and perhaps most fundamental mystery of all, the question that lies at the heart of every other puzzle we've explored: what is dark matter? For all our talk of halos, density profiles, and cosmic scaffolding, these structures are merely the shadow, the magnificent effect. The true prize is understanding the cause, the fundamental particle or particles whose collective gravity has orchestrated the entire history of the universe. The properties of dark matter halos are not just consequences. They are a complex set of clues, a cosmic cryptogram that we must decipher to finally identify the universe's most elusive constituent. Each class of candidate particle makes a distinct set of predictions for how dark matter should behave, and therefore how its halos should look. The leading contender for decades has been the WIMP, the weakly interacting massive particle. The elegance of the WIMP lies in its connection to known physics. Many theories of particle physics, most notably supersymmetry, naturally predict a stable, massive particle that interacts only through the weak nuclear force and gravity, making it an ideal dark matter candidate. WIMP are cold dark matter, meaning they moved slowly in the early universe, which allows them to clump efficiently into the small-scale structures we see in simulations. The success of the cold dark matter model on large scales is a powerful point in the WIMP favor. However, the very same small-scale problems we've discussed, the missing satellites, the cusp core issue, and the too big to fail problem, could be interpreted as cracks in the WIMP paradigm. These tensions have motivated physicists to seriously consider a wider and more exotic menagerie of possibilities. One particularly compelling alternative is the action. Unlike the massive WIMP, the action is predicted to be an incredibly light particle, but it would be produced in such overwhelming abundance that it could still account for all dark matter. Actions are a different class of cold dark matter, but with a unique quantum mechanical twist. Because of their wave-like nature, these ultra-light particles would have a de Broglie wavelength the size of a small galaxy. This would lead to a fascinating effect. On scales smaller than this wavelength, action dark matter would resist being compressed, creating a natural pressure that would smooth out the centers of halos and prevent the formation of those problematic dense cusps. In other words, actions could naturally solve the cusp core problem that has plagued the simplest WIMP models, all while preserving the large-scale success of cold dark matter. Then there are the sterile neutrinos. These are hypothetical heavier cousins to the standard neutrinos we know, but unlike their interactive siblings, they would feel only gravity, making them perfectly dark. Sterile neutrinos would constitute a form of warm dark matter. They would be lighter and faster moving than WIMP in the early universe, which would have a smoothing effect that suppresses the formation of the very smallest dark matter subhalos. This would naturally lead to fewer dwarf galaxies, going a long way towards solving the missing satellites problem. The challenge for this model is to be warm enough to explain the lack of small galaxies, but not so warm that it prevents the formation of any structure at all, a delicate balance that experiments are actively trying to probe. The true nature of dark matter could be even stranger than these well-known candidates. Could it be that dark matter is not a single particle but a composite object, similar to atoms made of protons and neutrons? Or perhaps it's part of a hidden dark sector with its own rich set of particles and forces, a parallel universe of physics that interacts with our own only through gravity. Some theories even suggest that dark matter might have a small electric charge or interact with normal matter through a previously unknown, incredibly weak dark force. The detailed structure of halos, particularly their central densities and the abundance of their subhalos, provides the testing ground for these wild ideas. For instance, the self-interacting dark matter model, designed to address the cusp core problem, would require just such a dark sector force to allow particles to scatter off one another. The grand task for the next generation of experiments is to use the cosmic evidence provided by these halos to guide the search. Particle detectors buried deep underground are listening for the faint ping of a WIMP colliding with an atomic nucleus. Laboratory experiments are using powerful magnetic fields to try and convert actions into detectable photons. Telescopes are scouring the skies for the telltale X-ray signature that could be emitted when a sterile neutrino decays. And gravitational wave observatories might one day detect signals from primordial black holes, another exotic but not yet ruled-out candidate for dark matter. Each observation of a dwarf galaxy's rotation, each map of a cluster collision, and each new simulation of halo formation is another piece of the puzzle, helping us to narrow down the possibilities and inch closer to a final answer. The dark matter halo is both the question and the answer, the enigma and the key. By studying its every property, we are not just mapping the invisible architecture of the cosmos. We are conducting the largest particle physics experiment in history, one that uses the universe itself as our laboratory. From the ghostly grip that holds spinning galaxies together to the vast, invisible rivers of the cosmic web, the 25 mysteries of dark matter halos reveal a universe far stranger and more magnificent than we ever imagined. We've journeyed through the cosmic detective story of the missing satellites, where predicted legions of dwarf galaxies failed to appear. We've grappled with the cusp core problem, a fundamental disagreement between what our simulations predict and what our telescopes see in the hearts of dwarf galaxies. We've confronted the too big to fail conundrum, where the most massive subhalos seem to have vanished without a trace. We've seen how identical halos can host breathtakingly different galaxies, from majestic spirals to dead ellipticals, and discovered the universal blueprint that dictates the internal structure of every single halo from the smallest to the largest. We've pondered the phantom halos that may drift unseen through the void, the fuzzy boundaries that define a halo's edge, and the mysterious symbiotic relationship between a supermassive black hole and the invisible giant that hosts it. We've unraveled the timeline of their formation, from the first seeds born of quantum fluctuations to the ancient behemoths that challenge our models of cosmic growth. We've traced the epic journey of the missing baryons, the atoms that should be there but aren't, and witnessed the bullet cluster's stunning proof of dark matter's existence. We've explored their varied shapes, from perfect spheres to cosmic footballs, their silent spin, and their fundamental role as the knots in the cosmic web. We've considered the radical alternative of modified gravity, the subtle cosmic bias that means a halo's history is just as important as its mass, and the epoch of reionization, when the first halos lit the universe aflame. We've even peered into their ultimate fate, from slow evaporation to the terrifying possibility of a big rip. And through it all, we've returned to the central, driving question: what is this stuff? Is it a WIMP, an action, a sterile neutrino, or something even more exotic from a hidden dark sector? Each mystery we've explored is not a dead end but a signpost. The missing satellites, the cusp core problem, the satellite planes, these aren't failures of our models but precious clues. They are the universe's way of whispering hints about the true nature of its dominant component. Solving any one of these profound puzzles wouldn't just answer a single question. It would rip open a portal to a new physics, revolutionizing our understanding of gravity, particles, and the very fabric of reality. These 25 mysteries show us that we are not at the end of discovery, but poised at the very beginning. So we turn the question to you, having journeyed through the evidence and the enigmas. Which of these profound mysteries captures your imagination the most? Is it the ghostly halos we cannot see, the silent planes of satellites, or the ultimate identity of the universe's most secret ingredient? Share your thoughts below, and let's continue to wonder at the dark architecture of the cosmos.